Hi everyone, thank you for invitation. I feel nice to present my work today. I'm going to tell you about one of the possible ways to decide problem of identical code section analysis with AFL. I hope that my results will be useful for other cybersecurity experts. My name is Maxim and I'm a student at National Research Nuclear University. This work was done as my bachelor thesis in collaboration with my supervisor. He's an independent security researcher and he has been exploring operating system security for more than 10 years. And today I'm going to tell you about fuzzing and some famous types of fuzzers. I will think of main fuzzing strategy which should be implemented to provide good fuzzing results. Then I will consider a classic fuzzing scheme based on AFL. In the next step, I will show you how to decide identical code analysis problem due to proposed tool. Finally, you will be able to watch test results of the tool, and at the end of my presentation, I will say some words about future plans of project development. Fuzzing is a popular method of program analysis. It's a technique of automated testing when a program receives specially modified and incorrect data which can lead to its emergency state or undefined behavior. Of course, with the help of fuzzing, it is possible to identify a large number of bugs and at least a large number of vulnerabilities. Programs that implement the fuzzing process are called fuzzers. There are different types of fuzzers. For example, fuzzers associated with network, the operating system kernel, drivers, web applications, and local application software. This classification depends on fuzzing goal. If it is needed to know input data format, then it is white box fuzzer. On the other hand, black box fuzzers allow us to fuzz programs without input type information. The fuzzing strategy includes the following main stages. First, static code analysis and determination of the attack surface. Then, selection of the primary corpus that contains the input data which provides the greatest code coverage. After that, reducing the size of the queue so the coverage doesn't change, a standard fuzzing cycle execution, and finally, analysis of identifying bugs and crash analysis. Let's say a few words about AFL. This is American Fuzzy Loop, one of the most popular fuzzers. With its help, a large number of vulnerabilities were discovered. According to classification, AFL refers to white box, source-based, and feedback-driven fuzzers. This means that to analyze the program code using AFL, its source code and information about input type are required. This is especially important for fuzzing with a dictionary. However, we didn't use a dictionary in our work. Let's look at such a simple model when the fuzzer starts a standard cycle. The fuzzer extracts an element from the queue and mutates it, checking the execution traces. Execution trace is a sequence of basic program blocks which have been visited due to a certain set of input data. This is implemented using edge instrumentation. This means that when moving from one basic blocks to another, an ordered pair AB of base blocks called a tuple is detected. It often happens when a fuzzer spends a lot of time analyzing identical sections of code without increasing coverage and without finding new bugs. At the same time, most of the code may not be investigated. This is unacceptable, especially when the fuzzing process is quite long and can sometimes last a day. We call this problem as identical code section analysis. This slide shows a simplified diagram of the proposed fuzzing system. It differs from the classical AFL scheme by the presence of a module that allows a person to manage the fuzzing process of AFL during the process itself. The difference lies in the user common interface for interaction with the module. Next, let's look at the process in more detail. Receiving the run command from the user, FuzzPy sends control signals to the fuzzer, starting the AFL fuzz process with certain parameters and report table update time. During this time, the fuzzer performs a standard cycle, retrieves the next element from the queue, mutates it, tests the program response, updates the queue, and displays a status window for the expert. At the same time, the specially instrumented has new bits function writes traces. When report table update time is over, FuzzPy stops the process, reads the traces, and determines such characteristics as coverage productivity. The results are represented in the form of the report table. The operator analyzes the data in the report table and sends a command to resume the process or redirect the flow. We can redirect the execution flow by selecting the operator, analyzes the data in the report table, and sends a command to resume the process or redirect the flow. We can redirect the execution flow by selecting an element from the candidate list in the report table. The candidate list was defined by the module at the previous stage. These are key elements that have not been tested yet or have comparative better characteristics, as they can potentially increase. At the same time, unexplored elements have a high priority as they can potentially increase coverage. Having selected an element from the list, the operator, having selected an element from the list, the operator sends a command to the module, which modifies the queue order and makes appropriate changes for the fuzzer service variables to avoid conflict. Finally, file with traces is cleared, the AFL fuzz process resumes, then the cycle repeats again. Now, I want to show how to detect trace. At the instrumentation stage, a random integer is generated in each base block of the program, called the base block label. When moving from one base block to another, the label of the directed tuple is formed by applying the XOR operation and the right shift. AFL uses a special array in which one label corresponds to the address label of the tuple that in the track. To detect the trace, we instrumented the hasNewBits function, which updates the trace bits array at each iteration. After AFL process start, the user receives status window and the report table. Experts interacts with the module with the command line interface. The main field of the table is part_conf. The value of this variable is defined as the ratio of the new unique tuples number to the number of runs on the current element. This is called coverage productivity. The module was checked using the TIFF library utilities, which are designed to work with TIFF files. It's known that many utilities of this library contain a large number of vulnerabilities. Therefore, this library is quite suitable for testing the module and comparing it with other AFL-like fuzzers. AFL and AFL Fast were chosen as such fuzzers. The fuzzing time is 12 hours. This is not enough to have quality program fuzzing, but it is quite enough to test the module as the utilities have already been tested by the developers. The report table update time is 30 minutes. The fuzzing results are shown on this slide. For each utility and each fuzzer, the total number of unique crashes and total coverage were determined. Analyzing the results of the graph, we can conclude that the proposed fuzzing system in the most cases finds crashes faster than other fuzzers. In future, we plan to consider the aim of using the proposed solution with static analyzers by adding a visualization module. This will significantly reduce the search space, as well as improve the interactivity of the fuzzing process. We don't exclude the using of machine learning elements, as well as adaptation of the approach for other fuzzers. We also strive to make the deployment procedure simple for different platforms. Thank you for your attention.